Okay, so today let's do we come to one of the highlights of the course, the LR rule in terms of paths. So maybe first let me tell you some different versions of this. So you have this S, so lambda is a partition, and you've seen S lambda, right? What is this? This is the Shor function corresponding to lambda, right? There are various expressions for this. One which, for example, Ravinder wrote down, which is some determinant by a certain determinant. That's one definition of it. Another definition is Amri defined it as you look at the sum of the weights of all semi-standard Young tableau of shape lambda, okay, and where n is fixed. Okay, so with fillings from 1 through n where n is fixed for him. Okay. So and that will be a symmetric polynomial in 1 through n, and it is this polynomial, right? So if we multiply two of them, so mu is also a partition, lambda mu dot 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 are partitions. Okay. So that is another symmetric polynomial in n variables. Okay. And one of the things Amri mentioned is, as you vary over all partitions with at most you can, if I am fixing a certain n, which is the number of variables, then since remember semi-standard Young tableau means the column, it is column strict, and I am filling from 1 through n. So the moment it has more than n rows, I cannot, it's not possible to have that. Okay, so when we are having n variables, naturally we are restricted to looking, S lambda will only make sense or will be non-zero only for when lambda has at most n parts. Okay, and the statement is that as you vary over all partitions with at most n parts, the S lambda will form a Z basis for all symmetric polynomials in n variables, or if you want, that will be an infinite module, but I mean infinitely, what is that, free module of infinite rank. If you want to just do it over some finite dimension, I mean, you can just concentrate on symmetric polynomials of a given degree d. Okay. Then you look at all partitions with d parts and at most n rows, and you vary over all such things. Then the S lambdas will form an integral basis, that is basis over the integers. Okay. There are very many different bases for symmetric polynomials. Perhaps these are the most interesting. Some of them, for example, the power sums, Newton's power sums, are only over the rationals. They are basis over the rationals, but not over the integers. Okay, but this is over the integers. Okay, so this is a symmetric polynomial, and what is its degree? Its degree, if lambda has a certain size, if lambda is a partition of d, then S lambda is of degree d. If mu is of degree has size e, then S mu is of degree e. So, when I multiply them, I get a symmetric polynomial of degree d plus e, right. And therefore, if I look at all partitions with at most n parts with exactly of the number d plus e, or with d plus e boxes, in other words, that set forms a basis for all symmetric polynomials of degree d plus e. Therefore, I must be able to write this as a sum of where nu is a partition of lambda plus mu, right. Is this notation make sense? And where c, lambda, mu, nu are some integers, okay. They are in fact non-negative integers. We'll come to that. Okay. So this is they are integers for the moment. Okay, they are integers for the moment, and so you have this problem, which is at a high school algebra kind of problem, right? Okay, and here is. So, this is one version of the Littlewood-Richardson rule, okay, just multiplication of symmetric polynomials, multiplication of sure polynomials, and expressing the product as a linear combination of sure polynomials again. Okay, these in other words, these are called the structure constants for multiplications of sure polynomials. Okay. So, but we also saw that S lambda is the character of V lambda. There is a corresponding irreducible representation of GLN, if you wish, or SLN. And then maybe it's better to take GLN because and there is one for V mu, right? And this is realized as the character of this is realized as the character of this, and therefore, and it's easy to see that the character of a tensor product is the product of the characters. So, this is the character of this, right? And by the semi-simplicity of my category, this is a direct sum of C lambda mu nu V nu right, where these are the multiplicities. I am just denoting it like this. Okay, maybe you want to write this on top, but you understand what I am saying. Okay, so now these numbers must be the same. Why? Because characters determine representations. Okay, so this is a representation theoretic. So Lie algebra, or GLN representations. To be very precise, one should say polynomial representations of GLN. Never mind, it works very well if you take GLN. You have to, do some adjustments if you work over SLN. We will see when we come to the rule. Okay, this is one version. There is yet another, at least two other versions of this, two other interpretations of this rule, and again very, very important. Okay, one of them is in the representation theory of symmetric groups. Okay, so suppose lambda has d parts. Okay, suppose lambda has d parts, and mu has e parts. sorry, lambda has d parts and mu has e parts. So it's a partition. There is a certain, what Amri this morning was calling the spect module. If you don't recall this construction, doesn't matter. All that is relevant is the irreducible representations of a symmetric group SD over SD, meaning over on D letters, over the complex numbers, is there are as many as there are partitions of D. Okay, so given a partition of D, I can associate to it a representation of SD, the symmetric group SD. Right? Okay. Given mu, I can associate a representation of SC, to symmetric group. Okay. Now, if G and H are groups and these are representations, their tensor product is naturally a representation for the product group. Okay. Okay. Now, this sits inside SD plus E in a natural way. Right, where the first D parts are permuted according to this permutation and the next E parts are permuted according to the other representation, other permutation. Okay. So, and this is a subgroup within this, right, clearly. So, this subgroup consists of all permutations of D plus E elements, where the first D are permuted among themselves and the next E are permuted among themselves. So, there is no switch between the first and the second. That is this subgroup. Okay? Okay. So, now you know that when there is a subgroup of a group, finite group, you can induce the representation of the subgroup to the top group. So, you induce this SP lambda tensor SP mu from this SD cross SC to SD plus E. Right? Okay. And you want to write this as a, now you want to write this as a direct sum of irreducible representations for SD plus E. And how, what are they indexed by? They are indexed by nu. Nu is a partition of D plus E. Okay. This also comes out to be the same answer. Okay. So, decomposing in or decompose in SD cross AC SD plus E into irreducible representations. Okay, that is yet another interpretation. There is another interpretation, this time geometric. Okay. So, I will just be brief here. So, there is this object called the Grassmannian. So, given two numbers m and n, m less than or equal to n, you can talk about the Grassmannian of m planes, m dimensional linear subspaces in an n dimensional subspace. Okay. Now, I am sure you would have seen when m is equal to 1. So, the case m equal to 1 is what? Is the case of the projective space, right? All lines in a vector space of dimension n is p n minus 1, right? The project space n minus 1. So, and you would have seen how to how to put a topology structure, even an algebraic variety structure on projective space, right. So, similarly, you can put a projective variety structure on these. Okay. These are smooth varieties, in fact homogeneous varieties, in the sense that there is a transitive group action. Okay. In fact, these you can realize this as GLN or GLM plus, I hope I get this right, GLM plus N, sorry, GLN mod some P. Okay. There is a realization of this just by, so if I look at m-dimensional subspaces in n-dimensional space, right, GLN naturally acts on the n-dimensional subspace, and it acts transitively on the m-dimensional subspaces. Given any m-dimensional subspace and given any other, there is an element of GLN which will carry this to that. Okay. So, the transit action is transitive. So, you fix a certain point and look at the stabilizer of that. That turns out to be a parabolic subgroup, what is called, and this quotient is therefore you can naturally identify, right. So, this is what is called a non-singular projective variety, okay. And then it has a cohomology. You want to study the cohomology of this, and there are some particularly nice classes in this cohomology ring, namely there are Schubert classes, in the cohomology in H star GRMN, let us say with integer coefficients. Yeah, you can just, both are the, it's not any different. That you can consider this as topological. So, but there are, using the differential geometric structure, you can, you know, we are talking about singular cohomology here. You can do that because it's a smooth manifold. You can take the de Rham cohomology and that will be equal to the singular cohomology, yeah, by de Rham's theorem. So, there are different models. You can choose the de Rham cohomology if you wish. Sorry, de Rham cohomology of course would be with complex coefficients, when you take complex or real coefficients. Here I am taking integral coefficients. Okay. Yeah. So, when you tensor this with C, you will get the de Rham cohomology, with R you will get the de Rham cohomology. Is that okay? Yeah. Anyway, this is all, we are not getting into the details here. I am just, so there are some particular classes. So, this is a, you can, as a Z module, these form a, this is a free Z module with this as basis. Okay. And then cohomology being a ring, you can ask for, when I multiply two of them, so it's a ring with a particularly given basis, just like that. This symmetric, Schur polynomials are a basis for the ring of symmetric polynomials. Similarly, here for this ring, these classes form a basis, and so I can multiply two of them and try to express them as the product as a sum. Okay, and what do you see? Again, you see these same numbers coming up. Okay, of course, there is some, you have to interpret this correctly. There is an m and a n. You have to let something go to infinity, etc. There are, we are making this kind of adjustments everywhere, right? Okay, but similarly, you have to make something here. But this is another. Okay, so there are at least these four different ways of looking at this problem. Okay, is this, so we are solving the path rule that we are giving, you can think of it as a solution to any of these as well. Okay. Okay, now let's actually, without further ado, let us state and prove the path version before we look at examples of. So what we'll do is I'll now state and prove it, and then we'll look at examples. So it's easiest if also because the paper introduces this notation. So let me just introduce some notation, some further notation. So Z pi. Okay, so recall what pi for us is. So again, we are in our now back to our usual notation. I have fixed G a symmetrizable Kac-Moody algebra, and I am considering paths. Okay, so pi is the set of all paths. And this Z pi is the free Z module on all paths. Okay, it's a horribly big module. Okay, Z pi. Now I will A is the subalgebra of end Z pi generated by E alpha F alpha. So what does that mean? E alpha F alpha act on pi, the set of paths, right? Of course, some of them they can either give me another, when I act E alpha on a path, I could get another path, or it could be 0. Okay. Now I can think of, I can make E alpha act on Z pi, right? So it acting on a basis element, either it takes me to another basis element or it gives me 0. Okay. So is this clear? When I say generated by E alpha and F alpha, I am thinking of E alpha as an element here now in this end Z pi, which is in the obvious way. Okay. Okay. Now let's also introduce. Is this clear? Okay. One more notation, M pi. So recall was what was B pi for us, right? Yeah. So if yes, if you have a basis going to basis or to 0, then you have a natural that you can extend it on the free object generated by that, and that's what we are doing. Correct. Absolutely. Okay. So B pi, this is for pi in pi plus, right? Especially for this. B pi is what now? Is the colored directed graph containing pi, right? Generated by pi. Okay. And M pi, so M pi is the Z B pi, which is contained in Z pi. Okay, and so some more trivialities. One more triviality is that there is this map, right? Pi cross pi to pi. I have this pi comma eta going to pi star eta, right? So So let me take pi. So now one more bit of notation before we can state the theorem. Right? I take pi and mu, say, pi prime in P plus, right? So m pi star m pi prime. So this gives me a map like this, right? Okay. So this m pi star m pi prime is the submodule. So let's give this a name, maybe psi is the submodule, okay, psi m pi tensor, m pi tensor m pi prime of z pi.
So you had a bilinear map, from there you are getting that linear.
Here it is only at the level of sets. If you want, if I write a cross here, then that will be a bilinear map.
No, I am saying when you go, usually when you go from tensors, so from bilinear map you get a linear map when you go.
Correct.
Tensors.
Correct.
Here also is happening like that.
Is happening like that. Yes, exactly. So here is at the level of sets. If you, and I have jumped to the linear map, as you say. If you want a bilinear map in between, you would have written z pi cross z pi to z pi. Right? That would give you a bilinear map from which I get this linear map on the tensor. Absolutely. Okay. Okay? Pardon me? This is Z modules. This is just as a Z module. Okay? This is just as a Z module. Okay. Now, one thing to observe is, okay, so thanks for talking about A modules, I had forgotten. M pi is an A module. A submodule. Of Z pi. Why? Because B pi is closed under the root operators. Okay? I mean, see, this is rather silly. I mean, we are not doing anything extra. We are just, but it's convenient to have this language. Okay, that's why. I mean, it's completely silly. We are not doing, I repeat, we are not doing anything deep. Okay, we are just setting it up. That's all. So is this okay? M pi is an A submodule. Okay. Now here comes the important thing. Now I claim this is a, so now it is not so trivial. So m pi star m pi prime is an A submodule of Z pi. So, observe, let me say claim. Yes. Exactly. It is just a statement of E alpha acting on, if I take E alpha on pi, 2, so this is because, because B pi I hope you understand what I mean by this. Is closed under the root operators. Why so? So, if I take eta here, concatenate with sigma here and say act f alpha here, what is this? So, one of the things, yes, so this requires the fact that if eta and sigma have minimal integrality property, MIP, then it goes into one of them. Okay, maybe to the left, maybe to the right, doesn't matter, it goes to the one of them. Okay, but now we proved by the colored graph isomorphism, first of all, by the statement made by Vishwanath, maybe I will prove it in the next 3 days, or maybe not. But in any case, Lakshmibai Sheshadri paths have MIP. This is a statement made by Vishwanath, right? And we proved following that as a corollary of the isomorphism theorem, on the very first day when I started lecturing, I think, I proved that that any element of B pi has minimal integrality property. Okay? So, this is because, so this is, let's equal, this is equal to f or eta f alpha sigma. Okay, similarly for E alpha. Okay, the reason is, one more, because B elements of, or B pi, let me say B pi has MIP, meaning every element of B pi has the minimal integrality property, and that is because of the colored directed graph isomorphism and LS pi 1 has MIP. Okay, is it clear? It's a long chain of arguments. So, this is something Vishwanath stated. Okay. It takes a bit of work to say that they have the minimal integrality property. Okay. Now, as a corollary of the, and even this, so there are several things we concluded from the colored directed graph isomorphism theorem, namely that there is a unique path on which all the E alphas vanish, namely pi itself. There is every path in B pi is obtained from pi by acting a sequence of f alphas. Okay, these two were rather immediate, but then for the minimal integrality property, we had to do this expansion business. So this was not, so even this because has some content in it. Okay, I'm just reminding you, we did this in the beginning. Okay, so is this okay now? Is the claim okay? Is the claim okay? Okay. We are almost now through. Now we are going to get our theorem. Okay? A minute. Okay. So now let us look at this, or let's look at this. Right? So I start applying E alphas, say, right? I start applying E alphas, and then can I apply them indefinitely? So I apply one E alpha in a whatever sequence. It goes to one of the, either the first or the second. Okay, I take another E alpha, apply it, goes to one of the second, take another, and so on and repeat. Can I go on indefinitely? No, no, because see, it has to go either here or here, and any element here is obtained from the pi 1 by a sequence of, so any element here, okay, I mean, so here is pi 1, right? It's some lambda, right? And I take some element, let's say eta in here, its ends somewhere, and this thing is a sum of, this difference is a sum of alpha is simple roots, correct. Okay. Now each time I apply a E alpha, I go up, I mean the difference shrinks, right? Okay. So I cannot possibly take E alphas indefinitely, right? So after applying several of them, I must necessarily be done. Okay. So what that means is, suppose so what I can do is I can look at all this, the set of all these paths, and take to each one of them, I can try to push it up, right? I can try to push it up so that I cannot apply E alpha anymore. Correct? I can do that. Okay. Okay. Then let's look at this process. So with every path, what I try to do is attach to it a path, to every path here, I attach to it a path in that B pi, in that concatenated space, on which I cannot apply E alpha anymore. Right? Okay. So I'm just giving a map now. Okay. So I'm given a path, I'm attaching the path. Right? Okay. Let us look at this process. Okay. Now, suppose I start from a given path and I applied certain E alphas and got myself a path on which I cannot apply E alpha anymore. Okay. Okay. Now maybe you started with the same path, applied a for all alpha, all possible alphas. So this on the top one, nothing should be applicable. It should be killed by all, it should be highest weight in that sense, it should be killed by all the E alphas. Okay. Okay. So you take, suppose you and I play this game, we start from the same path, but you choose your own set of E alphas. Okay. So you take a different, you take some other E2 maybe and apply it, E3, whereas I applied E1 and E4, something like this. Okay. And you went and got to a, so you start from here, and I start with this eta, right? Okay. And after applying, I got to some path. Let me call it, what's a good notation? Theta, right? So theta is again of the form something, let's call it theta is equal to eta prime, sigma prime, okay, such that E alpha on theta is vanishes. Correct? Okay. Mind you, I am not saying E alpha on these individuals vanish. Okay? I am only saying E alpha on theta vanishes. Okay. Okay. So maybe you started from the same path, applied the E alphas, and you got yourself to theta prime, let's say theta double prime, let's call this theta, original path, is eta double prime. Is this possible that these two are different? Okay, the claim is no. But why? Why is that? Correct. You have to show that, but you have to prove that. Okay. Well, here is the proof. Okay, that you end up at the same place. Okay. So why is that? Pardon me? Yeah, there is some coming back. That is the argument. Okay. Look at this. Right? Look at this. What can you say about it? Everything has the minimal integrality property.
This is actually precisely because you are demanding that for all alpha.
No, that does not give you a proof. That in itself does not give you a proof. Of course, that is necessary.
We can say like this. We can go from there to there. Theta dash and theta dash, double dash. So these endpoints, both of them are Weyl conjugate.
Are?
Weyl conjugate.
In what sense? They are not Weyl conjugate.
We had proper that in B pi. We had that they are Weyl conjugate.
No, not Weyl conjugate. Not Weyl. Weyl conjugate is a different thing. Weyl conjugate means in particular they have the endpoints are Weyl conjugate. Okay, that's a different thing. So there is a Weyl group action. There is a Weyl group action. Okay. Okay. So this is a very important thing. Why I am claiming they are the same. Okay. This is a very important statement. Okay. So pay close attention. So what does theta prime or theta double prime look like? Right? It is a path with minimal integrality property because everything in, it's okay. One observation is each of B pi and B pi prime have minimal integrality property, and then it's triviality to see if two paths have minimal integrality property, their concatenation has minimal integrality property. Okay, that's a very trivial thing. Okay, that is, of course, here you're also using that the endpoint is integral. Okay? Okay. But anyway, that is part of the minimal integrality property condition. We talk about minimal integrality property only for paths in pi int, which have endpoints as integral. Is this okay? Okay. So every path here has minimal integrality property. Okay. So theta prime has minimal integrality property. So theta prime and theta double prime have. Is this okay? Observation. Now, if a path has minimal integrality property and you apply E alpha on it and it vanishes, that means it lies entirely in the dominant Weyl chamber. Because if it did not live in the dominant Weyl chamber, it would, on some alpha check, so one of these graphs, H alpha, when you compute, it would come below 0. And the moment it comes below 0, because of the minimal integrality property, it would have to hit -1, in which case you would be able to apply E alpha on it. Okay? So, theta, so here, Shavik, what you said is correct, that this is for all E alpha it is 0, but along with the fact that theta prime has minimal integrality property. Yeah. So, have minimal integrality property and E alpha theta prime equal to E0 equal to E alpha theta double prime for all simple alpha. This implies, so let me write theta prime here. Thus, theta prime comma theta prime What I mean is that the images live completely in the dominant Weil chamber. No, that's also in the dominant Weil chamber. Where, huh? Correct. It could be one of those thetas. It definitely could be one of those thetas, but we'll come to that in a minute. That's a very interesting question. She's asking whether theta is always pi concatenate pi star, pi prime. That definitely is a candidate for this theta. Huh?
One of them will be pi concatenate.
Yes, one of those paths. So you start with various paths here and try to go up and obtain these thetas, what I am calling thetas. Of course, if you started with pi concatenate pi prime itself, which is a valid path here, and when you would end there, right? Okay, but you could start with something else and you could end there. Okay, but we'll see in a minute that it's not necessary that we start with anything and we don't need to end there. Okay? Okay. So this is completely contained in the dominant Weil chamber, which means what? That, look here, now I'm going to prove. So now theta prime is equal to theta double prime by an argument using CDG isomorphism. Okay, corollary of, using corollary of. Okay, here is the argument. You got this by applying, starting from here and applying E alphas, right? So you should be able to get this by applying F alphas from here, right? And you got this by applying E alphas, right? Which means that within this, if I start with B theta prime, right? You can talk about B theta prime. That contains theta double prime. But in B theta primes, because this is completely contained in DWC, there is a unique path which is killed by all E alphas, namely that itself.
That is not directed graph isomorphism, right?
Which one?
That everything is killed by that. That they have that property that B pi.
That is it is not, it's using corollary of. I said, that's why I corrected myself. It is not the colored. So the colored graph, directed graph isomorphism, the corollaries were the three important things. One is that in that B pi, there is a unique path which is killed by all E alphas. Every path is pi and then applied a string of F alphas. And finally, everything has a minimal integrality property. These are the three important things. We have used them all crucially. Okay? Right? We have used the minimal integrality property here. Right? Because and I have used the fact that this is obtained by F alphas, etc. Okay? So is this okay now? Okay. So now let's do this again. You take paths here, right? And now to each one of them, I can associate a path of the type theta. That is, E alphas will be killed on that. Okay. And now, after having said this, doesn't matter what path you took. If we started out with the same path, right, and you applied your set of E alphas, I applied my set of E alphas, and got to some point where we couldn't apply any more E alphas, you and I will end up at the same point. Okay? Okay. So now you can divide this into this, you can put an equivalence relation on these paths, right, using this. Namely, two paths I call equivalent if I end up at the same point. Right? Okay. So to each element of B pi associate a theta in B pi such that theta lies in the dominant Y chamber, okay, and the path we started with belongs to B theta. Correct? Okay. So now this gives a partition of this, right? Because this is an equivalence relation. If you and I started from the same point, sorry?
Each equivalence class became a mode for real part A.
Sorry, I didn't follow. Each equivalence?
Equivalence class became a model for
Absolutely. Absolutely. Correct. Okay. So what we have is B pi so theta belongs to B pi, and that theta lies entirely in the dominant Y chamber. Correct? That's what we have. Okay. Now I can write B theta here because this this is closed under E alpha F alpha. So once theta is there, all the things are there. Correct? Do you agree with this? Okay? Yes. So given an element here, what does it mean? It is obtained, it is obtained from theta by applying E alphas and F alphas, right? But theta is already here. We have obtained, this theta is obtained in there, and it's closed under E alphas, F alphas. Is this clear? Okay. So the conclusion, therefore, and now here is the jump. So using this, you can write m pi tensor m pi prime breaks up as a direct sum m theta. Theta is above. Now let's take character. So how does the character behave? So this is just m pi tensor m pi prime, right? See, the concatenation, if the endpoints will add, right? So please tell me, when I take character, what do I get? Character of m pi is what? Character of v pi 1 tensor character of is equal to sum over all theta is above character of v theta 1, right? So we have gotten what we want, right? And since characters determine representations. So we will get V pi 1 tensor V pi prime 1 is equal to theta as above. We'll look at this more closely. That's why I'm writing theta as above V theta 1. I mean direct sum if you wish. Okay, now let's look at theta more closely. What is the property of theta? Yes, Shamik. But why is the character of M? Okay, the definition by M character is, so M, what is M? M consists of Z linear combination. So if you want, so character of M pi is equal to character of B pi. That's not a sure. Huh? M pi is just the integral span of B pi. Okay, so given a subset of paths, right? Given a subset of paths, S, let's say M sub S is the integral linear combination of the formal linear combinations, finite linear combinations of elements from that S. And its character is defined just for thing as. Is this okay? Okay. Is it any? So the M pi is just a, it's just a silly thing, but it. Okay. Yes, it's a fact, yes. I mean, here is how you do it. So, just like for a finite group, right? So what you need to see is that the characters are linearly independent in a certain sense. Okay, because if I take a vector representation, decompose it into irreducible characters, sum of irreducible characters, sum of irreducible representations, then its character will be just if it is V1 to the R1, V2 to the R2, it's R2 character V1, R2 character V2, etc., plus R2 character V2. Now, if I have another representation which decomposes as V1 into S1, V1 power S1, etc., I will get S1 character V1, S2 character V2. But if the characters are linearly independent, then S1 is equal to, correct? If the characters are equal, that means S1 equals V1, S2 equals, S1 equals R1, S2 equals R2, etc., which means, but those were the multiplicities of the irreducible representations. So, so you have to show that the characters are linearly independent, and that's rather trivial because each time there is you pick up they go more and more. This lambda highest weight, you can use that to show that. So given a bunch of characters, look at their highest weights and look at the highest of them, and you can then use that. By that argument, you can show that it's easy to see. It's rather lies at the surface. Yes. Yes. First, you have shown that it's a semivisible category, and that's Hermann-Weyl's theorem. Okay, which you can also prove using this Unitarian trick. You can reduce it to the compact group case and do it. Okay.
That is only in the case of finite dimensional setup.
Correct, absolutely. That is only in the finite dimensional setup. You prove, it's proved in Kart's book, that integrable highest weight, I hope I am saying it correctly, integrable highest weight representations of G. Huh? Okay, yes, correct. Yeah.
But you separately prove the length of the
Yeah. Okay, is that okay? Okay. So theta is above. Let's look at theta as above a little more carefully, because that's a very important set for us. Okay. So what does this mean? I look at all concatenations, one of shape pi, another of one in b pi and another in b pi prime, such that E alpha on that is 0, right? Okay. Now, if so how does E alpha act? So look at the first path, right? If it starts coming out of the dominant wide chamber, if the first path comes out of the dominant wide chamber, then I can apply E alpha on it, on the entire concatenation. Because if the moment a path starts, if for some h alpha it starts going down, right, that means I can apply E alpha to it. Of course, it has to have the minimal integrality property, which in this case it does, right. So no matter what the concatenation is, if the initial path, right, if that is, so I take my theta is of the form eta concatenate sigma, where eta is in b pi, sigma is in b pi prime. Okay. Now, if eta is not completely in the dominant wide chamber, then neither is eta concatenate sigma. Therefore, E alpha is applicable on that. Okay. So both, first one has to be. Okay. That is that clear? It has to be. First one has to be lie entirely in the dominant wide chamber, and therefore it has to be pi, because the only one that lives completely in the dominant wide. If it lies completely in the dominant wide chamber, it means E alpha is non-zero on that. There is a unique path in b pi on which all the E alpha vanish, namely the pi itself. So theta is above, you can write it as pi. So sigma such that sigma is in b pi prime and lives in the dominant wide chamber. Okay, you can write this more simply, because so this pi lives entirely in the dominant wide chamber, right? So for this to live entirely in the dominant wide chamber, all you need to make sure is what happens. The sigma lies entirely in the dominant wide chamber, but what is happening to sigma? Sigma is shifted up by pi 1. Okay, so this you can write as sigma plus pi 1 plus sigma, right? By this I mean sigma shifted by pi 1 lives in the dominant wide chamber. Okay, and so that is our LR rule. Okay, so okay. Path LR rule. So let me write it now. V lambda, just in this language, tensor V mu is equal to V. Okay. So what I do is I look at all paths in, so if you want, lambda plus sigma 1 where sigma, if you is in B pi mu, or okay, pi prime, where pi prime is in P plus with pi prime 1 being mu. Okay, and lambda plus sigma completely lives in the dominant Y chamber. Just rewriting it. Okay. So all I do is, here is what I do. I have two highest weights, lambda and mu. Okay. Just like in the tableau case, this is asymmetric. Okay. You can choose lambda to be the first one, mu to be the second one, or the other way around. Okay. It does not matter, and it is not clear that you will get, it is not clear a priori that the right hand side is symmetric. Obviously, the final answer should be symmetric in lambda and mu, but this is not obvious from the expression on the right hand side. So it is a little asymmetric, okay, on the face of it at least. So what you do is you look at all paths of shape mu. By shape mu I mean, you understand what I mean by shape mu, right? Or LS paths of class mu as Vishwanath defined, or you take a path which lies completely in the dominant Y chamber and which ends at mu, and look at, apply F alpha to it as various strings of F alpha, see all the paths that you get, and one of those paths, right? So you look at only those which, when shifted by pi lambda, live entirely dominant. Okay. So this set of paths is, so another way of saying it, so such paths, such sigma are called lambda dominant paths in B pi prime. Okay. So you can say, you look at all lambda dominant paths of shape mu, right? See where they end. Add that to lambda. If I have 10 of them, then there are 10 different components, and I keep adding lambda to them, right? By shape of path, I mean just the end point. So think of a tableau. The shape of a tableau is just the partition which represents the highest weight. Okay, so it comes from that line, it's an extension of that. Okay, so let's do an example. Okay, so let's begin maybe with, I want to do several, you can do some wonderful examples, visually attractive ones, but let's do Amri's, yes, Venkatesh. Yes.
It's like you're starting with some weight and then you want to enter with a dominant. Here you are successfully applying E alpha.
Yes.
Do they have, from a preservation theory side, do they have any weight? Then you take the weight space and then apply the corresponding E alpha operator.
Yeah, no, that's a different ball game altogether. That's a different. So we believe that E alpha and F alpha are the shadows of X alpha and Y alpha respectively, or capital E alpha and capital F alpha depending on the notation you use, correct? But that is only, I mean, it's not, there are theorems which that's why we said No, we believe that it's a shadow, and to say that it's a how closely it is a shadow is each time you have to prove it. You have to prove a theorem. Okay, so for example, here is what you can try to do. Here is a natural question. So let's take this. I start with some lambda, which is pi 1. Sorry, lambda, and so I choose pi in p plus with lambda 1 equal pi 1 equal to lambda, right? Right. And then you know that you write this b pi, right? B pi is every element of b pi. So for given eta in b pi, okay, choose. Can you choose f string alpha 1 alpha s such that of simple roots such that eta is equal to f alpha 1 f alpha s pi. Of course, that is trivially eta is obtained like this, right? And but here is the crucial thing. Suppose I take this string. Now these are the Chevalier generators. Apply it to V lambda. And such that these form a basis of set notation. Eta is varying over b pi. So for every path, I choose a string.
So you have written first given eta in b pi.
Give so sorry for the okay. So it's okay. I think it's okay. It's not very well. Can you choose for each? Can you choose a string? Okay, such that first you attach a string to every eta, right? Such that the string, when I apply it to pi, must give me that eta, right? But when I apply the y alpha operators on the highest weight vector, I get some vector of that weight. Those must form a basis. Okay. Okay. Now this there are some solutions to this. There are some by Littleman himself and by several. Anytime you can solve this, it's a good theorem. Yeah, and there is not a unique solution. Maybe there are several solutions. What is? As I vary, is this okay or does this make sense? Yes, each time to each eta you associate a string such that eta is obtained from by applying that string on pi. Okay, that's of course there are many strings you can choose, but you should choose it in such a way for each one such that when I apply that same string of y alphas to v lambda and I get a set of vectors, they must be a basis. Okay. Of course, so this is only, you can, there are some immediate simplifications you can do. You can just concentrate on one weight space because these are all weight vectors, right? And they are the right number. So you can either show it's spanning or you can show it's linearly independent, etc. Okay. So maybe towards the end of this week, if the time permits and depends on how everything else goes, I'll show you how to construct one solution to this problem. So,
This is true. This is we can choose. You were saying.
no, I said, can you choose? Can you? Okay. No. Okay. Good question. No. Yes, I think so. If I'm correct, Littleman has produced such a has proved this, that you can choose. Okay, in the general case, but if at all I present it, it will be a simpler version. Okay, maybe that works for classical groups or just for SLM. Okay, because it is technical. So the paper to look at is there is a paper in Littleman, Journal of the American Math Society. I think he has just one paper in this, so it's 1998 around. And it starts with something contracting modules. That's the term. That's and dot dot dot. Okay. But we are not getting there. That's heavy on representation theory. It uses quantum groups. It uses various constructs. There is a lot of geometry representation theory there. Yes. No, there is not a unique path. Yeah, then of course you have no choice. Then you just ask, suppose I take this, will I get a basis? Yes, that's the question. Yeah. Okay, let's do some example. Okay, so you remember the Peary rule that Amri did yesterday and today? Okay, let's try to maybe do that using our new method. Okay, so what does the Peary rule say? If I take, so Peary rule, what he called the baby Peary rule. Let's do the baby Peary rule first. Yes. Of what?
Like p-pies. Suppose some relation among characters of
yes.
p-pi. And we know character of p-pi is character of p lambda pi 1. But from that can we deduce something about the
representation theory? Yes, very much. Very much. That's the whole game. So see, characters determine representations. That statement means, see, to check, for example, even just like for finite groups, to check that two arbitrarily, you may have realized two representations in entirely different ways. And if I want to say this is isomorphic to this, all you need to check is its characters are the same. It's if and only if. Right? Pardon me? Right. So remember, as I think Ravindra made this point, it's a very small, I mean, think of it as a fingerprint. Right? To check whether whether it's Shamik or not, I just need to say, show me your fingerprint. As long as I have Shamik's fingerprint with me, and I can just compare it against. I don't need to see his face. I only need to see his fingerprint. It's somewhat like that. Okay? Yes, they do. Yeah, that is, in fact, that's what we are doing here. Okay, so let's do baby-Pierre rule. Okay, so what was that? So if you remember, you take S lambda, right, and what do you multiply it with? Just one box, which is S1, okay, or x1 plus xn, and what do you get? This is sum of S mu was in lambda plus, something like this he wrote, right? Right? Okay. Let's just take some, okay, simple. So lambda is equal to, let's say G is equal to SL3 or something, okay, or GL3 slash, let me write if you want. And lambda is this, something like this, right? And so what does this lambda plus mean? So you take this box, right? You can put it either here or here or here, right? Okay. Now if this were like this, then you couldn't put it here. You could either put it there or put it here, right? Okay. Let's see what this means in terms of our let's get this as a special case of our rule. Okay. Now, so this is my lambda, this is my mu. It's good to choose mu to be the smaller one, right? Because we are going to be worried about parts of shape mu, and surely there will be much less of them if mu is the smaller one, right? Okay. So what is this mu? This is just the defining representation. Okay, this is just the defining representation of GLN or SLN, in particular of GL3 SL3. So what are the paths? What is the highest weight path? Oh, thank you. Thank you. Thank you. Thank you. Okay. So this is, so mu, so this is the character of V epsilon 1. Epsilon 1 is the highest weight of the defining representation. Okay. And what are the paths? If you take epsilon 1, again I am using our standard epsilon 1 this way, epsilon 2 this way, epsilon 3 this way. Okay. So what are the paths of shape epsilon 1? All straight lines, and they are epsilon 1, epsilon 2 and epsilon 3 if you are in GL3. Correct? Okay. Now where is this? So what do I have to do? I have to look at this lambda. Okay, lambda is some, let's say, m boxes on top, n boxes on the bottom. So that is m epsilon 1 plus n epsilon 2. Correct? Okay. So this is my dominant weight chamber. Okay. M epsilon 1, right, and then n epsilon 2. So this is m epsilon 1 plus n epsilon 2, where I've gone m steps this way and n steps this way. Okay, I can choose any path, Anyway, it's only the end point that matters. Okay, it's only the end point that matters. So what do I have to do? At that end point, I must place my paths of shape mu. Okay, and see which lie entirely in the dominant wave chamber. Okay. So if I place my paths here, the picture will look like okay, correct? Which of these are surely in the dominant wave chamber? If I go along the direction of epsilon 1, surely it's going to be in the dominant wave chamber. So that is adding it here. Correct? It will become m plus 1, it will end at m plus 1 epsilon 1 plus n epsilon 2. Okay. When does this belong to the dominant wave chamber or not? If n is less than m, there is still one step, there is still room here. But if m equals n, I am right on this, and then I cannot add it. So that matches exactly with whether I could add this whether I can add this box here or not depends exactly on whether n is less than or equal to m. N is strictly less than m, and that precisely is whether this ends here or before. Okay? Okay. And how about this? As long as there is one box here and one box here, I can add this, right? So actually, what is this? This will become, since epsilon plus epsilon 1 plus epsilon 2 plus epsilon 3 is 0, this actually becomes, if it's m minus 1 epsilon 1 plus n minus 1 epsilon 2. The way to interpret this is the following. So if I add here, okay, so remember this picture is for SL3. But SL3 representations should not have partition, the partitions corresponding to those must have at most 2 parts, right? But here I am getting a third part. I mean, something bigger. It's as if, so you ignore this. That's like a trivial representation. Okay? Actually, if you think about it in GLN, it comes out very, very nicely. It's as follows. What is this representation for GLN? It is the determinant, it's the one-dimensional determinant representation. Okay, so for example, if I take this and try to decompose it, okay, clearly the degree of that is 1 more. Correct? So the degree of this polynomial is 1 more than the degree of S lambda, because I am multiplying it by degree 1 polynomial. Okay? So all the shapes that I get must also have 1 more degree in them. Okay? So that 1 more degree is, so that's why in GLN it is a better thing to, so you add 1 here, or 1 here, or 1 here. Okay? As far as GLN is concerned, this is just this irreducible representation corresponding to this times a determinant, meaning tensor a determinant, tensor a 1. And that part is for SL3 when you restrict, that determinant reduced representation just becomes a trivial representation. Okay? It just becomes C, tensor, the trivial representation tensor. Okay? So that's how this thing works. So is this right? Yeah, you could add a box here, and so it would mean this. It would mean m minus 1 epsilon 1 plus n minus 1 epsilon 2. So what happens is, if I add it here, as far as SL3 representation is concerned, this is, you ignore this because for SL3 every partition must have the partitions that correspond to it must have at most 2 parts. So whenever you get a column of size 3, you ignore that. Is that okay? So what is left? M minus 1, n minus 1. Correct? So I started with m and n, added this one here, and removed this, which in effect means m minus 1, n minus 1, which is precisely adding this epsilon. Correct? You can work this out. Let's do, okay. Let's do one more. Maybe we'll come back to this. There is a little more to be said next time also. But let's do one complicated example and see. So here is, you remember okay, S to 1, right? This is our just take it for SL3 if you wish. Okay, this is we've seen this representation. This has been our running example, right? We've seen all models for it, semi-standard Young tableau of shape 2, 1, or Gelfand-Zeitlin patterns, or paths, the LS paths, or the paths of shape epsilon 1, epsilon. Okay, so compute do this. Okay.